In today's video, we are going to look at something I know we all can't wait to happen: the ways this coronavirus epidemic can finally end. But we're going to focus on how scientists are able to use math to make decisions. I'll preface this video by saying I am by no means an expert on the matter, but I will do my best to share what I understand about the situation. There are two things that can happen, apart from the virus staying around forever, kind of like the flu virus and how it is constantly evolving. But the first way is that we get a vaccine, which would indeed be awesome because the virus would eventually just go away. But from a math lover's perspective, this is pretty boring. So what we're going to do today is focus on herd immunity. Herd immunity refers to the resistance to the spread of a disease within a population that results if a sufficiently high proportion of individuals are immune to the disease. So what does this mean? Let's take a look at a very simplified graphic where we see a row of people at the bottom. And in this row of people, everybody can only infect the person directly to their right. So let's say the first person gets sick, and then he gets the person next to him sick, who gets the person next to him sick, and on and on. But let's say the fifth person in the line has immunity. Let's say he was vaccinated. Since he is able to fight off the infection due to this vaccine, he is now much less likely to spread the disease to others. So even if the people to the right of him are not vaccinated, the spread of the disease is much less likely. This, like I said, is a very simplified explanation, but the main premise is if most of the population has developed immunity, even individuals who aren't vaccinated are offered protection because the disease has little opportunity to spread from person to person within that community. So what about how this relates to COVID-19? If we're unable to make a vaccine, some people are suggesting that we simply let the disease run its course until enough people develop natural immunity to the disease. In countries like Sweden, for example, they are asking the high-risk population, older people and those with underlying health issues, to self-quarantine, but is keeping many schools, restaurants, and bars open. They are hoping that majority of the low-risk population is able to fight off the disease and develop natural immunity, and therefore be a part of the herd that protects the entire population. And it'll be interesting to see how this turns out for them. I did promise math in this video, so let's start getting into some of it. I'm going to use an example of a disease that has already been more or less eradicated in the US, and that's mumps. But before that, let's define some terms. So we have R naught. R naught is the basic reproduction number. This is the average number of cases caused by an infectious individual when the entire population is susceptible. In other words, this is the number of people when a disease is first born and the epidemic has just started, and therefore no one has developed immunity yet. It is the number of people that will get an infection from one infected person. If we look at the disease with an R naught of 2, so if one person has a disease, that person can infect 2 people, and each of those 2 people can infect 2 more people for 4 people, and each of those 4 people can infect 2 people each. We can see how this exponential growth can quickly lead to an epidemic, provided the R naught value is greater than 1. The next term we're going to look at is R. R is the effective reproductive number. This is a more useful number for analysis as it is the true transmission rate of a disease. That is, it does not assume the entire population is susceptible anymore. So let's say half the population has developed immunity to the virus, and we can see how the graphic is adjusted. Now only 1 person is initially infected instead of 2, because that's half of 2. And then only half of what that person could infect is now infected. Now we can see only one of the people in the bottom row is infected. R mathematically is equal to R naught times the fraction of the population that is susceptible. We can then infer that if R is greater than 1, that the number of cases is increasing, as each person is infecting more than 1 person each, who is then infecting more than 1 person. And as initially, we can see how an epidemic can continue like this. When R equals 1 exactly, the disease is endemic. That is, it is constantly present in the group and it won't go away because the number of cases is not decreasing even though the number of cases is not increasing as when R was greater than 1. The dream is to have R is less than 1, so the number of cases decreases. Because each person is infecting less than 1 person, who is infecting less than 1 person, and this trickle-down effect eventually ends up with nobody getting infected. The last term we'll define is the herd immunity threshold, which is the threshold percentage, or the minimum percentage, of a population that needs to be immune for herd immunity to be acquired. Once this percentage of population is immune, R becomes less than 1 and the virus spread slows down. If we know the herd immunity threshold of COVID-19, we'll have the percentage of people we need to gain herd immunity in order to stop the epidemic. Let's look at how we can calculate a general form for HIT. We want R to be less than or equal to 1. As before, we have R equals R naught times X. Remember, X is the percentage of the population that is susceptible, and HIT is the percentage that we want to be unsusceptible to the disease. So we can define HIT as the percentage of the population that isn't X. So we can say HIT equals 1 minus X. Using some algebra, we can get X equals 1 minus HIT, and we can substitute this into the original equation. We also want R to be less than or equal to 1, so we can substitute this in also. Now, to solve for HIT, we can divide both sides by R naught, then subtract 1 from both sides. Now we multiply both sides by negative 1, remembering to flip the sign of the operator because we are multiplying by a negative number. We are left with HIT is greater than or equal to 1 minus 1 over R naught, which we can rewrite as R naught minus 1 divided by R naught. This gives us a convenient way to calculate HIT if we know the R naught of a particular virus. So now that we know how to calculate HIT, let's revisit the mumps example. The R naught of mumps, which is a pretty infectious disease, is about 12. So we have HIT is greater than or equal to 12 minus 1 over 12, or about 92%. So 92% of the population needs to be immune in order to stop the disease spread. Fortunately, we have a vaccine for mumps, so we can easily accomplish this number. For COVID-19, the R naught is estimated to be around 3, but we're not actually sure what the true value is, so we're just going to use this for this example. This means we would need about 67% of the population to be immune to stop the spread. This is an astoundingly high number to reach without a vaccine. This would mean about 220 million people in the country would need to have contracted the virus and developed immunity. And if we use a very conservative mortality rate of about 1%, this would mean about 2.2 million deaths. This is the reason scientists are stressing self-quarantining and flattening the curve. By flattening the curve, we are giving scientists more time to find a vaccine and/or a cure, so we don't have to have 200 plus million people infected with this disease. So let's shift gears a little bit and talk about how we can know what percentage of the population has developed immunity to the virus. You may have heard of antibody testing. This is a way to test if you have been exposed to the disease, but have been asymptomatic, so you've therefore built natural immunity and hypothetically can't contract the disease. For this analysis, we'll assume this to be true, even though scientists aren't sure if being exposed to this particular virus once means you have complete immunity. With statistical testing, there are two main concepts to keep in mind: test specificity and test sensitivity. Test specificity is the ability of a test to correctly identify those without immunity to the disease. So it is the ability to find true negatives, the rate that the test says the person does not have immunity and the person actually does not have immunity. A high specificity test will correctly rule out almost everybody who does not have the disease and will generate almost no false positives. Sensitivity refers to the ability of a test to correctly identify true positives. So it's the rate that a test says you are immune and you are actually immune. A high sensitivity test will correctly flag everyone who has the disease and will not generally generate false negatives. Specificity is a lot more important than sensitivity for COVID-19. The point is that false positives are worse than false negatives. People walking around thinking they are immune when they actually aren't would be catastrophic. So for the sake of the following example, we'll assume sensitivity is 100%, so we can look at varying effects of specificity. With that, let's dive into a modern version of a classic probability problem. A company boasts a 95% specificity rate and a 100% sensitivity rate. That is, an antibody test will correctly identify positives 100% of the time, and identify true negatives 95% of the time. So I take the test and I test positive, and we want to know what the probability is that I am actually immune, given that the disease prevalence is 4%. So if you want to pause the video and give this a shot for yourself, go ahead. Just a warning, the answer may not be what you think. With these types of conditional probability problems, I like to set up a tree diagram. We start with 100% of the population, and we can make two branches. The first is the 4% that has the virus, and the other is the 96% that is not infected. Of the 4%, there are two options. The test can be a true positive, meaning I have the disease, and the test agrees and says I have the disease. Or I have the disease, but the test disagrees and says I do not have the disease. Fortunately, since the test has 100% sensitivity, it will correctly identify true positives all the time. So the chance of a false negative is 0%. Now we examine the not immune branch. Like before, we have an option where a test gives the correct result and an option where it gives an incorrect result. But this time, we must look at the test specificity, which is 95%. So 95% of these tests will correctly return negative. However, 5% of the tests will falsely say I have immunity when I, in actuality, do not. We want the probability that I am actually immune, given that I test immune. We need only look at the two cases where the test comes back positive. The first is the probability of a true positive. This is the 4% chance that I was initially infected times the 100% chance of a true positive, so 0.04 times 1, or just 0.04. The second is the probability of a false positive. This is a 96% chance I was part of the population that was not initially infected, times the 5% false positive rate. This is 0.96 times 0.05, or simply 0.048. So now to get the probability of immunity, we divide the number of desired cases, so the true positives, by the total number of positive cases. We see that we get a seemingly unbelievable 40.8%. So it is actually more likely that I am not immune, even given that I tested positive. Obviously, we want the antibody test to be as accurate as possible. Therefore, scientists are actively trying to get the test specificity up to 100%. However, there's another important factor that determines the accuracy of a positive result, and that is prevalence. Let's use a dummy variable in the tree diagram from before to see why. Again, let's assume sensitivity is 100%. We can define P as prevalence and R as specificity. The 100% population is then divided into two groups. The one that has been exposed to the virus, and that'll be probability P, and the one that has not been exposed to the virus, with probability 1 minus P. The virus exposing group will be split as before, because the sensitivity is 100%. So we'll have 100% true positive and 0% false negative. The group that wasn't exposed will be split up into a true negative probability of R and a false positive probability of 1 minus R. Once again, we only care about the positive results here, so when calculating the probability of an accurate positive, our sample set will only include those. The numerator will be 100% true positive rate times the probability P that the person was in the virus exposed group. The denominator will be that P times 1 plus 1 minus P times 1 minus R for the false positive group. We can now set this equal to 100% or 1 because we want the accuracy of a positive result to be as high as possible. Multiplying both sides by all that stuff in the denominator and then doing some algebra, we get 0 equals 1 minus P times 1 minus R. So when P equals 1 and R equals 1, the test accuracy would be 100%. So we've already seen why specificity being 1 or 100% would be good, but now we can also see that as P gets closer and closer to 1, the test becomes more accurate also. What this means is antibody tests are increasingly more accurate in areas with super high prevalence and less accurate in areas where less people are infected with the virus. This is likely one of the reasons why everybody isn't able to get antibody testing right now. Many of the available tests are not FDA approved. That is, they haven't been properly vetted for specificity and sensitivity, and the prevalence of the disease isn't high enough to compensate for it. Don't forget to like and subscribe if you're new, and hit the bell to get post notifications so you don't miss a video. Also, please comment if you have any questions or suggestions for future videos, and we'll try to get to them.